All right, so in this new problem, we're going to solve another algebraic equation, which is also slightly perturbed. I probably forgot to write it before, but this is something that is obvious here. Epsilon is always a small number in what we do here. And we want to solve this, this problem. Okay, as you start facing a problem like this, there are two questions you first ask yourself. First, is it a problem that is singular or regularly perturbed? Okay, so what is the nature of the perturbation? Singular or regular? Think of it for a minute. To understand, we need to address probably the second point, which is the unperturbed problem. The unperturbed problem is what you get when epsilon is equal to 0. This is x squared minus 2x plus 1 is equal to 0. It has two roots. So does the perturbed problem. So the perturbation is regular in this case, right? Because the unperturbed has two roots too. And the two roots actually are, well, I mean, two roots. This is something to be discussed, of course, and this is what makes this problem a little bit more specific or different, is that if you want to solve the unperturbed, this is what you have. So in fact, this is only one root, but multiplicity 2. Okay, so the problem is not singular in the sense that we had a root coming from infinity exactly as before. All right, probably we can have a look at the problem again in a graphical manner. So if you want to specifically plot x squared minus 1, it looks something like this. This is 1. X squared minus 1. So there is one root. And what we do here is that we subtract, in the governing equation, what we do is that we subtract simply epsilon multiplied by x squared, right? We had x squared minus 2 plus 1, that's the unperturbed, and we just subtract that quantity. Oops. So this is a flat parabola passing through this point, like this, meaning that we should decrease this slightly. The function we're looking at, and it becomes like this. All right, it's just a sketch. And what we had before is one root with multiplicity 2. It is now split into two roots. And the problem we are facing here is called root splitting. All right, so because of the small perturbation, the root that had multiplicity 2 before becomes two different roots with multiplicity 1 each. Okay, and that's what we want to solve. It is probably not a big deal, as this still remains something that is regular, right? So probably let's give it a first try and try to use a regular ansatz as before. Regular ansatz. X is equal to x0 plus epsilon x1 plus epsilon squared x2, and so on and so on. We could even use here, we could even use the unperturbed. I do, of course, anticipate that this value should be equal to 1. It will come clear in a few seconds, but we can extrapolate that this is going to be the solution of the unperturbed problem, right? Because when epsilon is equal to 0, all of this needs to drop. So x is equal to x0. And we saw before that when epsilon is equal to 0, the unperturbed problem is that one, and the solution should be 1, okay? So you can use, if you want here, you can use x is equal to 1. There's definitely no problem with that. Or keep x0, and it should come clear in a few seconds or in a few minutes that x0 is equal to 1. All right, so let's just substitute this ansatz into the governing equation. So we have 1 minus epsilon here multiplied by x squared. So it's going to be x0 squared. I'm going to keep terms up to epsilon squared. All right, so x0 squared plus 2 x0 x1 epsilon plus x1 square epsilon square plus 2 x0 x2 epsilon square. Okay, that's for the first term, minus 2x0 minus 2 epsilon x1 minus 2 epsilon square x2 plus 1. And this is equal to epsilon to the third. Okay, let's try to collect. We can make it fast and do this collection of the different powers probably right away. So at leading order, what do we have? x0 squared multiplied by 1 over there. Then we have 2x0 here plus 1. And this is equal to 0. What does it say? Of course, we were expecting this. Hardly. x0 is equal to 1. Okay, let's keep going with the following order. We have 2x0 x1 times epsilon coming from here. We have minus epsilon times x0 squared over there. Then we have minus 2x1 over there. And this is equal to 0. We could probably keep going with the following equation, but let's try to solve this one first. x0 is equal to 1. And so, or maybe just, let me just rewrite this in a different manner. So we have 2x0 minus 1 times x1 is equal to x0 squared, right? You see from here to there, I have just pushed this to the right hand side. And in what remains, we see that we have 2x1 multiplied by x0 minus 1. And unfortunately, this doesn't work because x0 is equal to 1. And it just is gonna say that 0 times twice times 0 times x1 is equal to 1. So there's no way to determine x1. And on top of that, the equation, of course, is wrong because on the left-hand side we have 0. On the left-hand side we have 1. So it means there's something wrong over here. There's maybe just a way for this equation to be satisfied, though, is that x1 actually grows to infinity, right? This just tells us something. So the fact that 0 is equal to 1 is a hint and shows that if x1 goes to infinity, I don't want to write is of order of magnitude of infinity because that doesn't make sense. we can play a little bit with the rules, but not too much. If x1 goes to infinity, then you can probably revisit this as some sort of indetermination, right? As you know from calculus, 0 times infinity is something that can either grow to infinity, either be equal to 0, or even be equal to something different from 0 and from infinity. So this is an indeterminate case, and you can compute this. So definitely, this hints somehow that in order for the ansatz here to be valid, x1 should be very large. But there's no way, of course, x1 could be very large. There's no way x1 could be very large because we do expect that x1 should be of order 1. That's what we want. And the equations, they tell us x1 should be much larger and should grow to infinity. All right, so I don't know if this shows something to you. If you see something strange in what we did, then it means you're good, because it's not very easy to understand this kind of point. But if you could just figure out or realize at this point that this means that a sequence we have chosen is probably not the right one. It means that it goes too fast, right? Because we would like the second term to be something, and this something actually is revealed by this ansatz as x1 going to infinity. So it means that epsilon here is actually too small. We should have something between x0 and epsilon. All right? So it means that the right sequence is not a sequence in 1, epsilon, epsilon squared, and so on and so on. We have the wrong sequence. Okay, again, this is probably not cheating too much, but let's just have a look at the exact solution. All right, this is something that was helpful in the previous example, and that's something I don't want you to do anymore. As soon as we'll be in a full steady state regime with perturbation methods, in principle, we will never ever have to look at the exact solution. And keep in mind anyway that the problem that I will ask you to solve during the exam and the different tests doesn't have an explicit exact solution, right? In most cases. So you should be able to work out based on the perturbation methods. But in this case, let's just have a look because it's easy to do so. So the equation that we want to solve, it's actually can be rewritten in this manner, right? Because if we just push the yellow terms over there in the right-hand side, this is what we have. So it means that x minus 1 is equal to plus or minus square root epsilon times x, meaning that x is equal to 1 over 1 minus or plus. Let's just put it as we want. And that series expansion is 1 minus or plus, or again, let me just change because it's not really important, minus or plus epsilon, etc., etc. And so what do we see here? Indeed, we see that we had the bad sequence, and the sequence that we should have used is in fact 1 square root epsilon, epsilon, and so on and so on. That is the right sequence. Of course, and because the ansatz is just like a mask that you use to reveal a solution to a problem, then if we use that in the ansatz, revise the ansatz. If we use that in the ansatz, x0 plus square root epsilon, let me just use x1/2 plus epsilon x1, and so on and so on. Let's see if we can get something out of that, right? I need to substitute again this in the governing equation. Oops. Let's paste it here so that we have the governing equation with us. 1 minus epsilon multiplied by x squared plus 2 square root epsilon x0 x1 half plus epsilon x1 half squared plus x1 squared. Oops. And I think that's it for the first one. I don't want to keep them. Let me just check. So this is the square root of the first. That's the double product. Then we have the square of the second. Yeah, of course, I'm missing the double product. 2x0 x1 epsilon plus other terms. Then there will be minus 2 x0 minus 2 square root epsilon x1 half minus 2 epsilon x1 and so on plus 1 is equal to terms which should be, the next term is epsilon to the power 1 half, 2 halves, 3 halves, like this. At leading order, again, we balance the different terms of the equation. What do we have? We have this multiplied by 1 minus 2x0 plus 1. All right, so at leading, we have x0 square minus 2x0 plus 1. Okay, this is no big surprise. So we have x0 is equal to 1. The next order is in square root of epsilon. Okay, so what do we have? Well, in fact, oh, cool, in the first term, you see this one is multiplied by epsilon, so nothing will come out there except this multiplied by 1. All right, so from there, we have 2 x0 x1 half. And then from the second term, we have this, and that's it at the end. So we have minus 2x1 half, and this is equal to 0. Oops, you should think again, but in fact, no, because the fact that we use the right sequence is such that we end up here with 0 is equal to 0. Okay, it doesn't help to determine x1 half, but at least there's no big deal. Okay, so we are here at some sort of intermediate scale, and we need to rewrite the problem until the order of magnitude of the different terms in the equation is epsilon, in order to be able to determine the small shift in the root splitting. All right, so let's keep going until order epsilon. So in the first term, we have x0 square multiplied by epsilon. The term which is multiplied by 1 is x1 half squared plus twice x0 x1. Then we have minus 2x1, and that's it. This is equal to 0. Again, you see, we could fear that x1 is popping in over here, but no problem at all, in fact, because these two terms, they balance each other, so they cancel. And we find that x1 half squared x1 half squared, which comes with a minus. I'm sorry here. All right, because this is minus epsilon. No, this is plus. Sorry, this is plus x1 half squared, but this is here minus epsilon x0 squared. So the minus is over here. So we have x0 squared is equal to plus or minus x0. Great. x1/2 is equal to plus or minus x0. And that's great because look at that. There was just one root in the unperturbed, and this is exactly what we need. Two roots. Okay, so we have been able to model the root split in here. All right, and so if we limit ourselves to the first perturbation, to the root, then we will see that x is 1 plus or minus square root of epsilon. All right, and the next term, of course, will be something in order epsilon. Okay, so what does it mean? It means that we could determine that, in fact, the quantity by which the root is displaced because of that perturbation is nothing but square root of epsilon over there. Okay, so we cheated a little bit still here, right? Because we said, look at the exact solution. The exact solution actually hinted that the sequence should be like that. Then we used that in the ansatz, we revised it. We saw that it indeed works. So what we're just missing today is how to find the right sequence, all right? How to find the right sequence. And so to do this, there are different techniques which are not necessarily obvious. And this is why usually I would recommend you to try an ansatz. And if the ansatz works, then use it and you're fine, right? If the balance is great, you find what is called the distinguished limit, and you have the right balance between the different terms, and you can keep working with that. If you struggle finding the right balance, because sometimes this is epsilon, let's say to the power 3/2, or something even more exotic sometime, then there is a straightforward approach that you can use, which is a little bit heavy, as I'm going to discuss, and which will provide you the right sequence. So in order to find the right sequence, what you could say is that x is equal to x0, which is something you know, right? Because this is the solution of the unperturbed, plus some order of magnitude multiplied by x tilde, which is of order 1. So x tilde is something that is of order 1, and delta is something that is much smaller than 1. How smaller, we don't know, and that's precisely what we want to determine. We would like to get that delta is square root of epsilon. Okay, if this is order of magnitude of square root of epsilon, then we set delta exactly equal to square root of epsilon, and we put the scaling factor into x tilde. All right, so if we just assume this, then let's look at the governing equation. All right, so as before, substitute in governing equation. And so let me just rewrite the governing equation as it is on the top of the page right now, because this one looks quite interesting. All right. So x minus 1 squared, that's going to be delta squared x tilde squared. This is equal to epsilon multiplied by x squared. So this is 1 plus 2 delta x tilde plus delta squared x tilde squared. Then what you do now is find the leading terms. Okay, sometimes it's a little bit tricky to find, but you'll see that with practice, that's something you'll find very, very easily. In this case here, if you expand the right-hand side, then you have 3 terms on the right, you have 1 term on the left. So you could find the leading terms just by pairwise comparison again. Or you can just use deduction in order to deduce that some of them are definitely not leading. For instance, delta being something that is much smaller than 1, you see that this one can be neglected when compared to 1, and definitely this one can be compared to when compared to 1. So definitely these two terms, they should disappear, and you see that there are just two terms remaining, and so it just means that the two leading terms at leading, we will have delta square times x tilde, which is of order 1. So delta square should be of order epsilon. And it just, in fact, tells us that delta is of order square root of epsilon, so we can choose delta equal to square root of epsilon. And so it means that the right ansatz is, in fact, nothing but x is equal to 1, or x0 if you wish, plus square root of epsilon multiplied by x 1/2 plus something else. And something else will be another delta, let me just call it delta 2, multiplied by another x tilde, with x tilde of order 1, and delta 2 being much smaller than square root of epsilon. All right? You repeat the same story. You repeat the same development as what we did here. You substitute in the governing equation, write the different balance, and at the same time, you'll get x 1/2 and the order of magnitude for delta 2. All right, so if you do this, I skip details, probably is a good job for you guys to do it on your own. You will find, you should in principle find that x 1/2 at this stage is equal to plus or minus x0, which is plus or minus 1, exactly as what we had before. Okay, this is left as an exercise, but we did this already. But the most important part of the exercise is that you should come up with a conclusion that delta 2 is as the same order of magnitude as epsilon, which means that the sequence is progressively building up, starting from 1, then square root of epsilon, then epsilon, and you could keep going this way in order to determine the different terms in that sequence. All right, so I hope this was clear. This is a very important topic, so try to practice this. There will be a bunch of exercises that now you can use to just discover a little bit more and to practice by yourself. So feel free to try them and enjoy as much as you can, of course, and keep going.